All right, good day, one and all. This material is being made to explain organic chemistry as taught by Prof. Nkansa, explaining the aromatic compounds. Yes, and then a point of caution, this material is a supplementary material to that which is being done in the lecture hall, not an alternative material. So let's take note of that. And then if you need any clarification, please see any member of the academic board, GPSAK and UST for the clarification. Okay, so when we start teaching this topic, the first thing that we'll talk about is the introduction to the whole topic. And so we'll talk about the fact that organic chemistry will study the chemistry of carbon-containing compounds, right? But then at a point, it's not only carbon-containing compounds, other compounds can come in. That other compounds that contain carbon, and then other atoms can also come in to study. And then we'll talk about the different types of classification. The one that we are being taught in pharmacy school here is that we have two major categories. That's aromatic compounds and then non-aromatic compounds, right? Yes, and then under the aromatic compounds, you realize that we'll have a carbocycle and then heterocycle. The carbocycle will consist of a ring with only carbon atoms, and then the heterocycles will have rings with carbon atoms and other atoms inclusive, right? Other atoms like nitrogen, oxygen, sulfur. Good. So that is the whole narration. What is the whole narration? Good. Then right after that, we will go to functional groups. We'll start studying functional groups. So that is why I've added this page on the slide to talk about functional groups. Good. Now we have to understand functional group because they are the main players in organic chemistry. If you see a compound, always there's a group within the compound that is responsible for the reactivity or the property the compound has. And then usually that is the functional group. So for every compound you see, you should know the functional group to give you an idea of the behavior of the compound, right? Now, these are the basic functional group, which will be of importance to us among the lots that we have. The first one is alkene. We have alkene. So alkene is C single bond C, very simple, right? Yes, the functional group here, arguably, is the hydrogen atom because that is responsible for the reactivity. Then the C double bond C here will show us that we have an alkene. This is an alkyne. We have a benzene ring, very simple. If it's a substituent, we call it a phenyl. So the ones in parentheses will show us the names if the functional group are acting like substituents, right? We have an imine, we have alcohol, ether. So let's study these functional groups and know that when we see them in compounds, you'll be able to isolate them. With time, we'll learn about these functional groups and know the properties. But for now, identification is the key thing that we are supposed to do here. All right, good. And then when we are being taught, usually some compounds are isolated and then we are asked to go and find the functional groups. The first one is lactone. Right, so lactone is an ester, but then it's a cyclic ester. So we see the C double bond OO here. It's an ester. But then the ester we have here is a cyclic ester. Let me write. Good. So this is what I'm talking about. So this functional group is an ester, cyclic ester. Good. Okay. Then we have lactide. So a lactide will be like a lactone, a condensation of different lactones. So you realize that the ester group is more than one. The ester group here is more than one. So we have an ester group here and then an ester group here. So typically it's like a lactone, a cyclic ester, but then usually we are expecting the ester group to be more than one in that cycle, right? And so we have something like dilactone, trilactone, right? Yes. Now, what we are doing here is identification. We are not talking about properties. With time, we taught the properties and also when you see the compound, you'll be able to tell the property. But now we are doing identification. Good, good. I'm sorry. Now, lactol. So lactol, from the name, it actually shows that it's somehow like an alcohol, right? So this is the functional group. It's also cyclic. So you have an ether group, right? And then the next carbon or the adjacent carbon will have an OH group. That is where the O comes from, right? So just know that if you have an ether group and the next carbon or the adjacent carbon has OH, then we are talking about a lactol in a ring form, right? A lactol, very simple, very simple. Good. And the last one is a lactam. So lactam will be like a lactum, but then in this case, we have an imide. So instead of an ester, it's an imide, right? Technically, this one is an imide, but it's fine. It's a cyclic imide. Okay, so good. Now let's come to the chemistry discussion proper. So we are being taught the two types of fission that happens in chemistry. The two types of fission that happens in chemistry. Now, the first one here is called homolytic fission. Homolytic fission. That is breaking of a compound into two equal parts, right? Now, the compound we have here is Br2. Now, Br2 has a bond between the two bromine atoms, right? Now, what has happened here is that the bond has broken such that the pair of electrons being shared here, each atom will go with one electron. So what we are forming here is a bromine radical, or the normal bromine atom, right? The bromine radical. And that is the behavior of homolytic fission. So the two electrons in the pair here, each will be given to an atom. That is the equal division. Now, the arrow we use here is very important. We don't use a full arrow, we use a half arrow. So if you are talking about homolytic fission, we don't use full arrow, sorry. We'll use the half arrow. So that is what has been demonstrated here, right? So you realize that this is a half arrow, there's a half arrow. Very important. And always the arrow will move from where the electrons are traveling for to where the electrons are settling, right? Good. So the arrowhead will point to where the electrons are settling. Good. That is homolytic fission. And then this one is heterolytic fission. This is unequal sharing. And so the pair of electron will be given to one, and then the other atom will lose the pair of electron. So that is what has happened here. The pair of electron being shared here will be taken. So we are using a full arrow, will be taken and then will be given to the chlorine to get a negative charge. And then the carbon here will lose the electron to be positively charged. Very simple. So that's heterolytic fission. Good. Okay. So aromatic compounds. Now we are saying that the term was initially used to describe fragrant organic compounds such as benzene. Now, aromatic, so it's an English word that means it has fragrance. So initially, that was the whole definition of the word, that compounds that can produce fragrance. But now we've seen that there are a lot of aromatic compounds without fragrance. So that is not the focus again. We don't isolate aromatic compounds to only fragrance-bearing compounds, right? There are more compounds which are aromatic but are not necessarily fragrant. So that's it. Now, I give an example like benzene that was isolated from coal distillate. We have benzaldehyde that was isolated from almond. We have toluene that was isolated from tolu balsam. So these are the structures. Now, these are basic structures in organic chemistry, and we should know them. We should know them. We should learn them and then probably write them so that we can know how to draw them, right? So this is benzene, the parent or the prototype compound in organic chemistry. That's aromatic compounds. Good. And this is benzaldehyde. Benzene with an aldehyde functional group. If you go and check the functional group, you see this is the aldehyde functional group. So C double bond O, and then an H here bonded to any other chain, right? This is the aldehyde functional group. And then this toluene, benzene with a methyl group. Very simple. Okay. Then we are saying that currently aromaticity is not associated with fragrance, since several aromatic compounds have been discovered which are not fragrant. The chemical behavior of aromatic compound is different from other organic compounds. That's non-aromatic compounds. So we are treating aromatic compounds separately because their whole behavior is different from all the other compounds which are non-aromatic. And that's why at the beginning I said there are two major categories of organic compounds that we can talk about, as the aromatic and then the non-aromatic. Right? And then we are saying that benzene is the prototype. Benzene is the prototype of aromatic compounds, right? Yes, and then it's a solvent in the laboratories. That means it comes as a liquid, right, at room temperature, and then it has a side effect of causing leukopenia if you are exposed to it for a long time. Okay, so what are aromatic compounds? Now, this is a basic definition. We'll have another definition which is quite extensive. So we are saying that they are a class of compound which contain 6-membered benzene-like ring with few alternating double bonds. So this is a basic definition, as I mentioned, right? So basically, we are expecting to see in 6-membered benzene-like. So not necessarily benzene. Sometimes it will mimic benzene in so many ways that we'll talk about in the subsequent slide, right? So if you talk about aromatic compound, we are talking about 6-membered. Sometimes not also 6-membered. So yeah, that's why I said this is just a basic definition that will clarify with time. So 6-membered benzene-like ring with three alternating double bonds. Trust me, not all aromatic compounds have 3 alternating double bonds. There are other criteria that we'll also discuss, but this is the basic definition of aromatic compounds, right? Now, we are saying that the types of aromatic compounds we have, it can either be naturally occurring or synthetic. The naturally occurring ones exist in nature, right? So examples are estrone. That's this one. Now, if you study the structure, you realize that there's a benzene ring here that makes the whole compound aromatic. Morphine. Morphine has a benzene ring here, that's a phenol ring, right? And then it makes the whole compound aromatic. Now, we have other examples like nucleic acids and then amino acids and heme, right? Good. Now, synthetic. So the synthetic are the ones made in the laboratory. Example, paracetamol. Now, point of question, let's learn the structure of paracetamol because it's very basic. I feel every pharmacy student should know how to draw paracetamol. So we should learn the structure of paracetamol. It has a benzene ring here. So easily you can just relate that it's aromatic, right? Benzene with an OH and then NH2, COCH3 at the para position. So very simple. And then fluoxetine. I'm sure those of us who have done community pharmacy will know fluoxetine. Yes, it has 2 benzene rings, so quickly you can relate to it as aromatic. Now, as I said, for now, what we are doing is identification. So how you can identify and categorize the compound. The properties will come with time. Good. Nomenclature of aromatic compounds. So we are saying that a large number of non-systematic names. Now, usually in the scientific world, we use the non-systematic names, right? Mostly we use them. It is very easy for you to say acetophenone, aspirin, probably those names than when you are telling me, because the systematic name of aspirin is not really that. Even the systematic name of paracetamol is not paracetamol, it's a different name, right? So usually we prefer using the non-systematic name. It makes you familiar with your stuff. So that is what we are seeing here, that usually we use the common names, right? So instead of methylbenzene, we are saying toluene, right? It is very difficult for you to go. Then on normal day, people are saying methylbenzene, we say toluene, right? Good. So we use the common names most of the times, and that's what we are talking about here. So a compound like phenol, right? That is hydroxybenzene, but then we call it phenol most of the times, right? So you should keep these names. When these ones come up, you should know the compounds you are talking about. So this is phenol, right? Benzene with OH group. This is benzoic acid. That's benzene with COH group. That is a carboxylic acid functional group. This is aniline. Aniline is benzene with the amino group, amino functional group, or the amine functional group. This is okay. So the amine functional group, right? Not amino, amine functional group. Now, this is xylene. Now, xylene is a benzene ring with 2 CH3 groups, right? Because it's auto. Now, auto means they are in the 1-2 position, right? That is, if I'm counting, this is number 1, this can be number 2. So that is why we have auto xylene. But that means I can draw something like this. It means I can draw something like this, right? And this will still be xylene. Let me write the CH3. Without the CH3, it's still xylene anyways. So I can put the CH3 here. Let me put my second way to show it benzene, right? So this is xylene. But then this is not auto-xylene. This will be meta-xylene. Very simple. Meta-xylene. Good. Now, I can also have para-xylene. So xylene will just be benzene ring with 2 CH3 groups substituted, right? But then auto-xylene will show us the position of the 2 CH3 groups. Very simple. Then styrene, this is styrene. Styrene, I don't know if you can search for polystyrene. That's something that we use to cover newly bought gadgets or newly manufactured gadgets. And this is the basic structure, styrene, very simple. And this is acetophenol, right? Acetophenol. So a ketone, very simple. Good. So nomenclature of aromatic compounds such as derivatives of benzene can be dealt in 4 different ways. Now we can deal with monosubstituted benzenes, which are the simplest actually, if you ask me. Monosubstituted benzene, then we can talk about alkyl substituted benzenes. And talk about disubstituted benzene, and we can talk about benzenes with more than 2 substituents. Right, so the immediate examples down here are monosubstituted benzene. So we just name the substituent and then we make benzene the parent name. Very simple. So this is benzene with Br group. We call it bromobenzene. This is benzene with the NO2 group. That's nitro. So we call it nitrobenzene. This is benzene with the propyl substituent. That's propane that has lost a hydrogen. So this is called propyl benzene. And that is for monosubstituted benzene. So if I have benzene with chlorine on top, then I call it chlorobenzene. And because it's monosubstituted, we don't even show the position. Usually, you can take the number 1 because if I'm counting, I'm supposed to count from where the substitution occurred, right? So this should have been 1, and I'll count maybe 2, 3, up to 6 here, right? But because it will always be 1, we don't really show it. So we just see bromobenzene instead of 1 bromobenzene. Very simple. Good, good. Now, the next one is alkyl substituted. So the alkyl substituted, we have this rule that benzene ring has 6 carbon atoms, right? Now, if the alkyl group B substituted has a long chain or a chain length, that's an unbranched chain length, right? Or a straight chain length, which is 6 or less, then we will name it as a substituent on the benzene ring. But then if it's 7 or more, it becomes the parent and the benzene ring becomes the substituent. So that is what has been written here, that if we have smaller alkyl substituent, that is 6 or less number of carbon atoms, then the benzene is a substituent, right? The benzene becomes a substituent. It will be an alkyl substituted benzene. But then if we have it being larger, that's the alkyl group being larger, that's 7 or more. Now 7 means that it has more carbons than what is in the benzene ring. Then the benzene becomes a substituent on the alkyl group. So that's very simple. And then we'll have a phenyl substituted alkane. Let me be quick to add that if benzene is acting as a substituent, you call it a phenyl group. Phenyl group, very simple. So phenyl, right? Phenyl group, very simple. Very simple. Good. So an example has been cited here. Let's look at what is happening. If I number the long chain, I have 1, 2. Now this is CH2 into bracket 4. So it's like CH2, 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 CH2. So I know my number 3 will be here, now my number 4 will be here, my number 5 will be here, now my number 6 will also be here because I have 4 of the CH2s continuing. That's if I elongate it, then this will be 7. If you don't expand this, you get it wrong. But then you have CH2 into bracket 4. So the ideally is CH3, CH, CH2, 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 and then CH3. And then on this one, we have the benzene ring. On this one, we have the benzene ring, right? So that is just it. And then we are saying that because the carbons here are 7, that is more than the carbons in the benzene ring. And so the benzene ring becomes a substituent, in which case it will be called a phenol, or sorry, phenol, right? Good. So number 2, that's this one carbon, 2. So we make it 2-phenylheptene. That's it. I stick the parent name of the alkene here. Very simple. And then we are saying that should the substituent be benzene plus CH2, then we don't call it a phenyl, we call it a benzyl group. So benzyl will be a substitution, right? That's still a substituent. But then we have benzene plus CH2 group before it has the substitution or gets the substitution in parent chain. And then in that case, we call it a benzyl group. So let's take note of the benzyl, right? Yes. I think some compounds, one of the exams was benzyl bromide. So if you are supposed to draw phenyl bromide or bromophenol, bromobenzene, this is benzene with bromine. But then if you are supposed to draw, but it's a benzyl chloride, that means you have to get the whole benzyl group and then you add the CO to get your benzyl chloride. That is benzyl bromide 2S, the benzene ring CH2 and then Br. Very simple. Very simple. Okay. Good. Now the next one. The following prefixes are used for disubstituted. So now the next criteria is talking about compounds which are disubstituted, and then we use these prefixes. That is O2, meta, and para. Now O2 will be when we are talking about the 1-2 position. That is the two substituents are adjacent to each other, directly adjacent. So that is 1-2 position. Meta will be 1-3 position. Para will be 1-4 position. So if you look at this compound, if I'm numbering, this will be number 1, this will be number 2, number 3, number 4. I can also number such that the chlorine here will be number 1, this will be number 2, right? Good. You number such that you give the least numbers to the substituent. So I can't start number 1 here and give number 6 here. No, it's wrong because I have not given the least numbers to the substituent. Now, if you realize that the substituents are adjacent like this, that's 1-2 position, then we call it O2. So this compound is O2 dichlorobenzene. Very simple. So dichloro because we have 2 chlorine, and then the parent is benzene, of course. Now this is 1-3. So 1, 2, 3. You don't name through this side because it will give bigger number. It will be 1, 2, 3, 4, 5. So that is wrong. We can't give the higher numbers to the substituent. You have to number such that you give the least possible numbers to the substituent. So 1, 2, 3. So 1-3 meta, right? And then this is 1-4, which is para. Now let's look at the names too. So this is dimethyl benzene. That is metaxylene. I said xylene will be benzene ring with 2 CH3, 2 methyl groups substituted on it, right? And then this is benzaldehyde with chlorine. So it's para-chlorobenzaldehyde. Very simple. Very simple. Very simple. Good. So we are saying that when there are more than 2 substitutions on the benzene, they are named by choosing a point of attachment as carbon 1 and numbering the substituents on the ring to give lower locants to the substituents. In writing the names, substituents are presented in alphabetical order. So these are 2 different criteria they have given us. They are saying that if we have more than 2 substitutions, we should number it such that we can give lower numbers to the substituents, right? Very simple. Next thing is that irrespective of the numbering, we should make sure that we name them in alphabetical order. So let's look at the first criteria before we go to the second one. Now, for the first compound, I can decide to number from here. 1, 2, 3, 4, 5, 6. Okay. Now I can also decide to number from here. 1, 2, 3, 4, 5, 6. the last order I'm doing is I can also decide to number from here. So I can make it 1, 2, 3, 4, 5, 6. Good. So in the yellow instance, that means the substituent will be on 1, 2, and 5. 1, 2, and 5. So I have 1 plus 2 plus 5. Now that will be 8. Good. Now in the blue instance, the substituent will be on 1, that is 1, 3, and 6. So 1 plus 3 plus 6 will be 10. Right? Now in the last instance, that's the red, I'll have 1 plus 2, that's 1 here, plus 2, plus 4. And that will be 7. Now, per the rule, we are supposed to give the least numbers. It means I have to choose the first scenario. That is, I have to number from here. This one should be 1, and then 2, and then 3, 4, like that. Right? That is everything. That is everything. So that is how I will do it. That is how I will do it. So let me number correctly again. 1, 2, 3, 4, 5, 6. Good. Now, after numbering, the naming, this is methyl, it starts with M. This is bromo, it starts with B. And so, irrespective of the fact that this is number 1 and this is number 4, I have to still start naming from bromo because we are naming in alphabetical order. That is the whole argument, right? So, we have 4 bromo. And now, between the number and the letter, we use a hyphen. Between two numbers, we use a comma. These are basic rules that we should know. So 4 bromo, 1, 2 dimethyl benzene. Very simple. Very simple. Now in other namings too, because of the common names we have when we have a particular substituent, like if we have OH is phenol. So we can start naming from the phenol, numbering from the phenol, so that we can make the phenol the parent name. So sometimes it's not only about you numbering such that you have the least number. If there are important functional groups, what you do is that you start naming from the functional group and you make that functional group part of the parent name. And so instead of calling this benzene, we are calling it phenol. That means the numbering should start from the OH functional group. That is the whole argument, right? Good. We could have made a substituent like maybe hydroxy, but once we are doing a phenol, that means it has to start from here. The numbering has to start from here. So this is 1. Compulsorily, this is 1. So we check whether coming here or coming here will give us these numbers. And then obviously it is coming to this side. So 1, 2, 3, 4, 5. Right. So we have 2, 5 dimethyl phenol. Phenol will be 1. So we don't even have to add a number. Right. Now that's the same thing done here. That we've made toluene the parent name. That means the CH3 here, this is number 1. This is number 1. The CH3 here is number 1. So we can number in any direction, so that we give the least numbers. Per the distribution, either ways will give you the same numbers. That's if you go to your left or your right. Good. So we have 2, 4, 6 trinitro-toluene, right? Toluene because the parent, the CH3 is number 1, and then we have named it together with the benzene ring. Very simple. Very simple. Very simple. Okay, good. Now, questions for us to try. We are supposed to identify which compounds are O2, meta, and para. Now, this one is, the first one is meta, the second one is para, then the last one here is O2. Now, let's also try and name them, even though we have not been asked to name them. Very important, right? Good. Now, this one can be said, we can name it as toluene. So if I'm naming it as toluene, I can say 3-bromo toluene. Very simple, right? Now, this one, I can consider this as the parent name. If I consider this as the parent name, then I'm thinking of benzene sulfonic acid, right? Benzene sulfonic acid. So this one will be methoxy group. So para-methoxy benzene sulfonic acid, or 4-methoxy benzene sulfonic acid. Very simple, right? Yes, and then this one, you can either choose either of them to be the parent, or you can name both of them as substituents. So if you want to go by phenol, then you get para amino phenol. Hey, sorry, not para. It's not para. It's O2 amino phenol. Very simple. Now we are supposed to draw these structures quickly. Let me draw them here. Para bromo. So I always draw my parent. That's the benzene ring. I draw my parent, benzene ring. Right. Good. Then they said para. That means 1,4 position. So bromine will be here, and chlorine can be here. I've changed the name. So chlorine can be here, bromine can be here. Very simple. Then the next one is toluene, right? So I'll draw my toluene quickly. I'll draw my toluene. So I always start by drawing the parent. Right? Toluene is benzene with CH3. So this is my toluene. Then they are saying para nitro. So on the para position, that's the 4th position, I'll put a nitro there. Very simple, right? Now aniline. The parent name is aniline. So I have to quickly come and draw my aniline. So aniline will be NH2, right? Yes, and then they are saying metachloro. So meta, 1,3 position. Then I'll put my chloro here. Very simple. Then yes, we have benzene. So let me quickly come and draw my benzene. Draw my benzene. Good. Now they are telling me that I have one chloro. So position 1, chloro is there, chlorine is there. Now position 3. So what is 1, 2, 3? Position 3, I should have a methyl group there. Now position 5, so I have to have a methyl group there. So 3,5 dimethyl. Very simple. I am done. No two ways about that. Okay. Good. Now the next question, they are asking us to name this one according to IUPAC. So in examination, Prof might necessarily bring common names because he doesn't really stress it. But then within this one, they're asking us to name it in the IUPAC way. So we have to be extra careful when naming these ones because they are quite. So we have to name them. So I can't say this is aniline. No, aniline is a common name, non-systematic, right? Good. So what I can say is that this is 1, 2, 3. So either way is 1, 2, 3, right? But now this is an amino group. As a substituent, we call this amino. Sorry, we call this amino. Then we call this nitro. So I can name this one as amino. A comes before N. So 1 amino, right? 1 amino, 3 nitrobenzene. Very simple. The next one I have to count and see the longest chain. So which one is the longest chain? 1, 2, 3, 4. Now you should also be careful because this one is CH2 because of the subscript 2 here into bracket 2 here. So I can bring another CH2 here just to make it clear. Right. So if I'm counting 1, 2, 3, 4. Now the carbons here are not up to 7, so we cannot even think of it as a parent. That means they have to be a substituent. But then if I'm counting from where the substitution occurs, this is number 1, this is number 2, there's number 3, and this is number 4. Now on the third one, on the third carbon, there's another substitution on the third one. So it means that is a substituent on a substituent, right? I'm sure Dr. Ponchiku has already taught us something like this. So this one will be 3 methyl, so that's into bracket. So 3 methyl butyl. 3 methyl butyl benzene. 3 methyl butyl benzene. So the butyl is the 4 carbons in the straight chain here. 1, 2, 3, 4. That's the parent substituent. It's the parent substituent. Good. And this is the substituent on that substituent. So the 3 methyl, we can write 1 here, but then usually we don't write that one. So position 1 on the benzene ring, we have 3 methyl butyl benzene. Very simple. Now this one to the IUPAC, we can start numbering from here. So 1, 2, 3, 4, 5, 6. Right. So we can have 1 amino, 1 amino, 4 bromobenzene. Very simple. Now if we come here, we can number from any place to the other. So this can be 1, 2, 3, 4, 5, 6. And then what I'll have here will be, this one is an ethyl group, is CH2, CH3. Right? So ethyl group. Now ethyl, nitro, nitro, E comes before N. So I can say it is 3-ethyl, 3-ethyl, 1,2-dinitrobenzene. Very simple, right? Then the last one, I can start numbering from here. 1, 2, 3, 4, 5, 6. So I'll have 1, 2, 3, 5. 1, 2, 3, 5. Tetramethylbenzene. Very simple. Very simple. All right, good. So let's move on quickly. Now, let's talk about the structure and stability of benzene. Structure and stability of benzene. So we are saying that the chemical structure of benzene is described by two theories, the resonance and the molecular orbital theory. So very simple, right? Now we'll talk about the two theories extensively, and then we'll see how we can use that to explain some of the properties. The other ones we're doing were identification. Now we are doing concepts. So we'll start appreciating some of the properties that even benzene has, right? Good. So you are saying there are two theories, the resonance and then the molecular orbital theory. Now we said the empirical formula of benzene was known, but then we didn't know the structure. So we knew for long that benzene was C6H6, but then nobody knew the structure. It was Hückel who proposed that benzene is a cis-membered ring, carbon atom ring that's containing single and double bonds. So Hückel brought the structure, the A. Now I realize that they are saying that the molecule oscillates between two equivalent structures, that's A and B, where single and double bonds continuously interchange. So now there are a lot of technicalities I have to explain in regards to these structures. The first one I have to talk about is the arrow here. Now the arrow is two-headed arrow. This arrow is used to show resonance. That is equivalent structures. Resonance. Right? We call them resonance structures. Right? Good. And so quickly realize that benzene is like this at a point, but then the double bonds don't really stay and the single bond don't stay at a place. They will move. So what happens at a point, this double bond will move here, this one will move here, this one will move here, and then also give you this. Now, these are not really different structures, they are similar structures. So the double bonds are continuously delocalized, the electrons are continuously delocalized, and then that resulted in this final structure called the resonance hybrid. The resonance hybrid. So all in all, the electrons in the ring are delocalized in a way. That is what has given us the circle. That is, they are moving. You just take it on the superficial, that the electrons are moving. So they are formed a circle. Right. So these are what we call the canonical structures of benzene. Canonical structures. And then the final one here, that's the one with the circle here, is called the resonance hybrid. Right? Hybrid means we have combined these two canonical structure, and then this is the structure that makes most sense. Right? At a point, benzene will behave like this. At a point, the double bonds will be here. But then what captures its entirety will be the hybrid. That makes most sense. Right? Good. Good. So we are saying that according to the resonance theory, right, the actual structure of benzene is a hybrid of the two Hückel structures, which leads to the resonance hybrid, which is the C. Now we are saying that each structure, A and B, is called the canonical forms of benzene. Very simple. Now, quickly didn't just come and see this. There were evidence that proved that what he was saying was true, right? The other things that his theory couldn't also explain. We'll talk about all of them. Now, evidence that support Hückel structure. We are saying that mono substituted benzene always gave one product. Now, if you add bromine in the presence of iron to benzene, we're always getting one product. Now, we getting one product, which is not even an addition product, but a substitution product, gave us an idea that, oh, okay, so then it means that if there were any other substitution on the benzene ring, right, at different points of bromine being added, we'd have had different products. But then look at this. If benzene comes here, it is bromobenzene. If the Br comes here, it's bromobenzene. If the Br gets monosubstituted here, it's still bromobenzene. If it gets monosubstituted here, it's still bromobenzene. So everywhere or each place where we get a substitution, we are just getting one product, which is the bromobenzene. So it showed us that, oh, okay. So then we have a reactant which is similar to this structure, right? That was just the idea. Very simple, very simple. Now we're seeing that disubstituted will give us 3 products. So if we put a substitution on the benzene and then we add another substitution, right? That's another substituent. We're getting 3 products, and then the products were at the auto, meta, and para. So it was also proven to us that what Hückel was saying was making a lot of sense, right? Was making a lot of sense. Good. Now let's take note of this equation, this particular equation, because even though you might not be taught the equations of organic compounds, or maybe how substitution occurs, the effect of substituents. I think one of our exams, this equation came. He asked us to write an equation between the aniline and then the methyl iodide. So let's just take note of this equation. Now you are getting 3 products. The 3 products will be the one at the auto, meta, and then para. So each of them, right? And then they can ask you to give maybe write equation that will support the Hückel's structure. Right now, these are the 2 that you should write: the monosubstitution and then the disubstitution 3 products. So monosubstitution gives us 1 product, disubstitution gives us 3 products. Very simple. Good. Now, limitations of Hückel. So we're also wondering that if it's an alkene, as Hückel is trying to make us see in the structure, then it should have undergone addition reaction. Funny enough, benzene does not undergo addition reaction. It undergoes substitution reaction, even when subjected to bromine. So it means he didn't really give us an explanation as to why it was undergoing substitution, not addition reaction, right? Good. Now, we are seeing that the Hückel structure does not account for why the carbon-carbon bonds of benzene have the length of 139, a value between the typical single bond of 154 and then double bond of 134. So we realize that if a bond is double bond, which is shorter, the double bond is 134. Now, if it's a single bond, it is 154. So we're expecting to see these different bond lengths in benzene, but then we didn't see. We realized that the value for the carbon-carbon bonds are all the same, and then they are all 139, which is between these 2. Hückel couldn't really give us any explanation as to why they are neither the length of the single and they are neither the length of the double, but they are in between, right? Good. So that is the idea. But then I think from what we have learned, you realize that the double bonds are not stationary, the single bonds are not stationary. There's actually a lot of delocalization, such that we wouldn't have a double bond at one fixed end. So because of the delocalization, what's happening is that it's like there's a measure of the double and single bond to form that hybrid. And so instead of getting a 154 or 134, we are getting something which is in between 154 or 134. I don't know if it makes sense, but it should make sense, right? That we are saying that the bonds are delocalized. You don't get a stationary double bond, you don't get a stationary single bond. So you don't expect to meet 154 and 134. What you expect to meet will be a mixture of them, and that is the 139, which is neither single or double bond, a mixture of them to give you something which is a hybrid. So that is the whole narration. But Hückel couldn't account for that. Now, the last thing is that Hückel structure does not explain why benzene molecule is unusually stable. Now, benzene is extremely stable compound, and then the Hückel structure didn't give us any explanation as to why that happens, and then that is another limitation, right? Now, we are saying that the resonance theory explains why the carbon-carbon bond lengths in benzenes are equal, and I think I've given a logical explanation as to why they are equal, right? And then the molecular orbital theory, which we are yet to do, right? We'll explain the other limitations, that is the stability and all, will be explained by the molecular orbital theory. So this is the molecular orbital theory. Now, the idea is molecular orbital. So we are talking about what happens at the molecular level. Very simple. Now we are saying that the carbon atoms in the benzene, each of them is sp2 hybridized. sp2 hybridized. That means there's an unhybridized p orbital. That is perpendicular. So there are very important things that you have to take note of regards to this. Now, when we're learning the normal quantum numbers, realize that if we meet one s orbital, we'll meet 3 p orbitals. 3 p orbitals. Now, if we talk about sp2, it means we have mixed one of the s orbitals and 2 of the p orbitals. It means there's a p orbital which is not used, That is what we are talking about here, that if each of the carbon atoms in benzene is sp2, as we can deduce from the structure, right, then there's an unhybridized p orbital. Now that p orbital is perpendicular, very important, as it meets the plane at 90 degrees. That means it's standing on the plane. That's in a layman's language, right? Good. Now, because these unhybridized p orbitals are perpendicular, they can overlap equally and well with neighboring ones. So if I'm supposed to draw carbon, 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 there's benzene, right? There's unhybridized p orbitals which can overlap. They can overlap, right, with neighboring ones. Now, because of this overlap, right, the 6 pi electrons, you realize there are 3 double bonds in benzene. Each of the double bonds has 2 electrons. Now, the 6 electrons are in pi bonds, so we call them 6 pi electrons, right? So the 6 pi electrons are completely delocalized. If we say they are delocalized, it means they are mobile. Because of the overlap, there's conjugation. Now, if we say something is conjugated, it means it is connected, right? Now, we are saying that each of the carbons have an hybridized p orbital, which will overlap. They are 90 degrees to the plane and overlap. Once they overlap, the whole system gets connected. The ring system gets connected. So electrons can move around. That is why we say the double bonds are not stationary. The electrons can move around, right? We are saying that the 6 pi electrons of benzene are completely delocalized around the ring, with the electron density all over, all in CC being identical. So because they are delocalized, the electron density in all the carbon bonds are equal. So it doesn't surprise us if we get a lot of that's the bond properties being the same, right? Because the electrons are delocalized because of the ring system, right? Good. Now we are saying that the delocalization of the pi system of electrons afford benzene the unusual stability. So benzene is also unusually stable because now usually what happens and brings the stability is because electrons are not really stationary. And then if they are stationary, if they are restricted in movement, sometimes they create a lot of repulsion that would lead to probably a lot of instability in the compound. Now, in this case, the electrons in benzene have been made to be delocalized, that they are mobile. That means they can move freely, right? Once they are moving freely, it gives them some level of stability. That is the idea that we are putting across here, right? Now, benzene molecule is therefore conjugated. Conjugated means it is completely connected, right? And that is because of the overlap of the orbitals and the subsequent delocalization. Now we are saying it's planar. If we say it's planar, it means it is flat. Now, when the orbitals delocalize as illustrated here, right, it forms something like it's more, it changes from being an atomic orbital to becoming a molecular orbital theory. And that gives it a certain flat shape. We say it is planar, that is, it is flat, right? That's when they overlap. You don't see them as the atomic orbitals again, you see them as molecular orbitals, right? And that gives that the flat shape. So that's still the overlap, right? Good. And then it has a regular hexagon shape. Very simple. Very simple. So these are simple things that we should get. Good. Now, the next one, we are saying that when the 6 p orbitals of benzene overlap, a molecular orbital, I've mentioned that already, is observed, right? 6 molecular orbitals are observed. Now, we are saying that when a given p orbital overlaps only with the neighboring orbital, localized pi electrons are formed. That is, if we have just a double bond here. Now, from last semester's topic, we should understand that if we have this, it means the first bond here is a sigma bond, the next one is a pi bond. Now, the pi bond is always formed when we have an overlap of two, I'm drawing this dumbbell shape to show the p orbital of 2 p orbitals. Now, we are saying that if we have just these two overlapping, then we get a localized pi bond, not a delocalized one, a localized one. That means it is stationary. That means the electrons here cannot move. They are stationary, right? Good. That they are stationary. Now, we are also seeing that there can be alternate double and single bonds, right, in a compound, but then it doesn't mean it's conjugated. The fact that you have alternate double and single bond does not mean you are conjugated. That's also something that we have to take note of, right? That the fact that you have alternate double and single bond doesn't mean you are conjugated. Conjugation implies probably more. There are so many anomalies that occurs. Good. So that is it. Now we are seeing why benzene is not an alkene. The basic thing that we have already encountered is it does not really necessarily undergo addition reaction, which is normal for every alkene. It will preferentially undergo addition reaction, not substitution reaction. Sorry, not addition reaction. Alkenes would have preferred to undergo addition reaction, but then benzene was preferentially undergo substitution reaction. So we are seeing that treatment of cyclohexene with bromine rapidly leads to addition product. So if I treat you benzene, this cycloalkene, right? Sorry, cyclohexene specifically. Now you get addition. That's the double bond will break. The double bond will break. That is the idea we are putting across here, right? But then in the case of benzene, what we get, we don't break the double bond, we form substitution. That is one thing that shows how benzene is not an alkene. Now, this is a question that can come. That's probably explain why benzene is not an alkene. Now, it's not an alkene because it does not undergo addition reaction. It will undergo substitution reaction. And we can use these two equations to just explain. Very simple, right? Good. Now we have to compare comparison of heat of hydrogenation of cyclooctatetraene, cyclohexene, and benzene. So we are just comparing them. Now the comparison we are doing here, the whole idea is to give us, that is to give us an idea. Right. So just give us an idea. So it's supposed to give us an idea of how stable benzene is. That's why we are comparing, right? Good. So now we are seeing that when 6-cyclooctene is hydrogenated to cyclooctene, 96 kilojoule per mole of energy is released. Cyclooctatetraene produce 410 when dehydrogenated. So let me when hydrogenated. So let me explain this. Now this is, let me draw the structures to ease the explanation. I'm talking about octene. So 1, 2, 3, 4. Let me see whether this can be my octene. Forgive me. So 1, 2, 3, 4, 5, 6, 7, 8. So this is octene. This is a different one. This is a different carbon, octene, right? Now this is the first compound, 6-cyclooctene, just one double bond. The next one that we are talking about here has 4 double bonds. So okay, so 1, 2, 3, 4. Right, good. Now we are saying that when we hydrogenate this one, it is 96 kilojoule per mole energy that we use. When we hydrogenate this one, it is 410. Now this is approximately 4 times of this. So let's say if this is x, this is approximately 4x. That is the whole argument. That's what we want to bring up. Even though it's not exactly 4x, but it's approximately 4x. Are we following? Good. So that is what happens in the case of octene. That's cyclooctene to octene, cyclooctene, right? Good, good. Now let's look at the difference in other scenarios. So good. Now hydrogenation. We are still talking about hydrogenation. Hydrogenation of cyclohexene produce 118 kilojoule per mole of energy, right? Good. So we are saying that if we have this is benzene ring. Okay, this is the one we talked about, the octene, right? Yes, this is cyclooctene, right? And this is cyclotetraoctene. So very, that's octatriene, sorry. Good. So this is what they talked about, right? Now we are saying that, okay, let me just use this picture. It will make it very simple. So we are saying that now this is a cyclohexyl ring with 1 unsaturation. If we are supposed to hydrogenate it, we use 118 energy, right? Now, if we have double, right, double of this, that's 2 unsaturation, we use 130, which is approximately twice of this. So in case of the third one, right, it should have been 3 times of this one. That was the whole idea. That was the whole idea. But then that is not what we observe. What we observe is that what we observe is that in this case, the 96 and then the 4 times was like just multiplying this by 4. In the case of the benzene, right? The first one and the hexene, the first one and the second one, the cyclohexene, sorry. The first one and the second one are also saying the same thing. That is 118. And this is like twice of 118. But then if you come to the benzene, it has a lower energy than even the 2. And that's what we have observed, right? And then that shows that, once you have a lower energy, you have a higher stability. That is always the narration, that's lower energy, higher stability. So the extremely low energy that benzene shows gives us an idea that it is what? It is very stable, right? And the amount of stability relative to what we expected give us the resonance stabilization energy. So we're saying that one of them is 118, right? Now 3 was supposed to be 118 times 3. Let me just do this. This is supposed to be 24, 4, 2. This is 5. This is 3. So this should have been the energy required in hydrogenation of benzene, but that is not the energy we require, right? And then the deficit between this one and this one gives us the extent of how stable benzene is relative to how we're expecting it. And that's what we call the resonance stabilization energy. So let me do the subtraction to know the deficit. Let me just do the subtraction. So this one is 14. So this is 8. Let's see if I have my subtraction right. This is 4. So 148. So we read from other reference that approximately 150 kilojoule per mole more stable. That's what we call resonance stabilization energy, right? And that is the whole argument that what we're expecting from the other observation that we have made, what we're expecting is not what we are seeing. So we are saying that hydrogenation of cyclohexene yields 118 kilojoule per mole of energy, whilst that of cyclohexane-1,3-diene produce 230 kilojoule per mole of energy. Heat of hydrogenation of benzene is 206 kilojoule per mole, approximately 150 less than the expected if benzene were an alkene. That is 356. Right. Now we are seeing that the extra stability of benzene is called aromaticity. The extra stability of benzene is called its aromaticity. That is the whole idea. Very simple. Very simple. Now we are coming to give a better definition of aromatic compounds. So when we started and we're defining aromatic compound, I said that is just the introduction to aromatic compound. We cannot draw conclusions from that. We are here to give a better definition of aromatic compounds. So let's talk about aromatic compounds. So we are saying aromatic system can be defined as planar, that is flat. Before we can say you are aromatic, you should be flat. You should be fully conjugated, that you should be connected, right? You should be monocyclic. That's if you're monocyclic, we are talking about you obeying the Hückel's rule, even though other cycles also, that dicyclic can also obey Hückel's rule. But monocyclic, strictly, you should obey the Hückel's rule, right? That is 4n plus 2. But the 4n, the n here are integral values, which correspond to the number of degenerate orbital pairs, right? Good. So they have given us 3 criteria. That is aromatic. If you say you're aromatic, you should be planar. Now there are so many questions which will ask, why is a compound said to be aromatic, right? Or why is it? So when that question comes up, the answer is that it is fully conjugated, it is planar, it obeys the Hückel's rule. These are the 3 main criteria which we base on to say something is aromatic. Very simple. So we are saying that the above rule is the Hückel's rule, right? Now let me state some things to make the Hückel's rule very simple for us. Let me state 1 or 2 things to make the Hückel's rule very simple for us. Let me write on this screen. Good. So now if n is equal to 0, we have 2, right? If n is equal to 1, we have 6, as in the case of benzene. If n is equal to 2, we have 10. If n is equal to 3, we have 14. So let's keep these numbers. Let's keep these numbers. Now these are supposed to be the number of electrons, that's pi electrons, that will show that the system is aromatic. That means either you have 2, you have 6, you have 10, you have 14, going onwards like that, right? Now benzene has 6. That means benzene obeys the Hückel's rule. Benzene is flat. We have said that already. Benzene is fully conjugated. Very simple, right? Good. Now we'll meet other ones that have 10 and 14 with time, but let's keep these numbers. That is how we use the Hückel's rule. We put numbers here, and then we get approximately the number of pi electrons that would tell us that you are aromatic. That's just the narration, right? Now we are seeing such systems have closed shells of electrons in all. Now, one thing is that usually aromatic compounds are in a ring form. I have not seen any open aromatic compound. So that's another thing. They are closed shells of electrons, all in bonding orbitals, and are exceptionally stable. That's one thing about aromatic compounds. They are stable, right? Now we have analogous systems with 4n pi electrons. So their rule is not 4n plus 2. They are 4n. And those ones are called anti-aromatic compounds. Now there are questions. I've seen questions where they have asked us, they have given us 3 compounds to actually categorize whether they are aromatic, non-aromatic, or anti-aromatic. Now, the anti-aromatic one, if you want to determine them, it means the A is what? 4n. That is, if n is equal to 0, we have 0. If n is equal to 1, we have 4. If n is equal to 2, we have 8. So these are, and then an example is cyclobutadiene. This cyclobutadiene. So this is anti-aromatic. So if he asks you to categorize it, you are wrong if you say it is non-aromatic. It's anti-aromatic specifically, right? So let's take note of that one too. Now you are seeing that note, cyclooctatetraene is not aromatic, even though it has 4 alternating double and single bonds. Now we said that the fact that you have alternating double and single bond does not mean that you are aromatic. We've made mention of that fact already, right? And then we are saying that cysteine-aniline also follows the Hückel's rule. That's the fact that you follow the Hückel rule does not also mean that you are aromatic. So there are exceptions. We can get compounds which obey the Hückel's rule and then are not aromatic. In the case of the cysteine-aniline, I want us to find the structure, but then they are saying there are a lot of ring strings that will destabilize the whole system, so will not make it aromatic, right? Yeah, the structure is, if I can draw it somewhere more here. So I have this. Oh God, you can find the structure. I'm just trying to draw it. Good. So we have here, and then here. So this is like the aniline, right? And they are saying that because of the lot of ring string in the structure, it's not really aromatic. Very simple. But then it obeys the Hückel's rule. So you are saying the fact that you obey the Hückel rule does not mean that you are aromatic. That is the whole point on this slide. Very simple. Very simple. So the structures have been given. I do it to show the ring string. This is the cysteine-aniline. Very simple, right? And then this is the cyclooctatetraene. Very simple. We say it has alternate double and single bond. It's not also aromatic, right? So we don't use just one criteria to see whether a compound is aromatic. Everything should come in place. Now we are saying that for conjugated systems that are not monocyclic, the case is a little bit different. So it is very easy when we are talking about monocyclic system, but then if you talk about something like naphthalene, right? Naphthalene is not monocyclic, dicyclic. You realize that the bond lengths are different. Yes, a lot of things will change, even though it still obeys the Hückel's rule because it has 10 pi electrons, right? Yes, but then a lot of things change there. A lot of things change. And then it also undergoes substitution reaction preferentially. It has 2 benzene rings fused together, but then it's less aromatic. So a lot of properties here. And then we are seeing that it can also be reduced to tetraline. Now the equation is here. Let's take note of this equation, right? Now the bond lengths are not the same. That's why we are seeing that if you come to cycles which are not monocyclic, a lot of complications will come up, right? Yes. Good. Now summary about benzene and benzene-like aromatic compounds. So you are seeing that the benzene molecule is cyclic and conjugated. The actual structure of benzene is the resonance hybrid. And so that's the best one, the most sensible one, right? Between the two canonical structures proposed by Hückel. The benzene molecule shows heat of hydrogenation as 150 kilojoule per mole, less than would be expected for the conjugated cyclic triene, making the benzene molecule usually stable. Right? So benzene is stable. Now the benzene molecule is clean and that's flat, and then it has a shape of a regular hexagon. Usually a lot of questions after concluding that it's aromatic, they will ask you, so what is the shape? So the shape, it is planar And then if in case of benzene or any benzene-like structure, we can say it's hexagon, right? Regular hexagon. But then it's planar. Usually, if they ask you what is the shape after concluding that it's aromatic, the next shape that you give that it is planar. Good. Now the bond angle is 120 because of the hybridization, which is sp2. sp2 is hybrid 120, right? Good. And all carbon-carbon bond lengths are equivalent. But then this is particularly true for monocyclic, dicyclic. There will be a lot of deviations that come up. Now we are saying that benzene molecule undergoes substitution reaction that maintains the aromaticity instead of addition reaction, because if it's supposed to undergo addition reaction, it will affect the double bonds inside, right? So it undergoes addition reaction and maintains the ring system, right? So it maintains the aromaticity. Then we are saying that it is consistent with the Hückel's rule. Very simple. Now, the compounds we are talking about are neutral compounds, but you can get ions which are also aromatic. That is the next table of discussion. Ions, and then we can have heterocycles which are also aromatic. So we are saying that ions and compounds which contain atoms of different elements as part of their ring can be aromatic, right? For a compound to be aromatic, it does not mean that the number of pi electrons must be equal to the number of carbon atoms in the ring. And that is not the narration at all. Right, so let's explore heterocycles which are aromatic, and ions which are aromatic. So all the atoms in the ring are not needed to be carbon before it is aromatic. So we are talking about that. This is supporting the fact that heterocycles can also be aromatic. We don't have to get all the carbons in the ring to be, all the atoms to be carbon. We can have nitrogen in the ring, but then the system will still be aromatic. We'll talk about those ones in no time. But then let's look at these structures. So this is cyclopentadiene, right? Now, this structure is not aromatic because of many reasons, right? The fact that these carbons are sp2, but then this carbon here is sp3. So that is the first negative thing. This is sp3. So it is not aromatic. Now, let's look about the Hückel's rule. This is 2 electrons, 2 electrons. So we have 4 pi electrons. Hückel's rule tells us that either we get 2, 6, 10, or 14 going on. So it means it does not also obey the Hückel's rule, right? Good. Now, when it's formed an ion, that is when we remove the hydrogen here. Now, the hydrogen here goes in the form of, hydrogen can move in 3 forms. Very important. It can go as a proton. Now, if it goes as a proton, it means it leaves the electrons here. It can go as a radical. That is when it undergoes fission, homolytic fission. It can go as a radical, right? That means it would take one electron and leave 1 electron here. Or it can go as an ion. As an ion. That's a negatively charged ion. Good. Now, when it goes, it means it takes the electrons away. So we'll see the behavior in all the other instances. So the hydrogen here will move. But then when it is moving, it will move away as a proton. It means it doesn't take any electron. Now, when we lose this hydrogen as a proton, that's as H+, the electrons are left here. Now, when the electrons are left here, after losing, the hybridization changes to sp2. That's the first thing. The next thing is that the electrons here will be contributed to the ring system. The ring system. So instead of having 4, we'll have 6 pi electron. Now, once we have 6 pi, it means you obey the Hückel's rule. Now, the carbon here is in the right hybridization, and then it has unhybridized p orbital to overlap with the neighboring ones. And so this whole thing becomes aromatic. So the cyclopentadiene anion is aromatic, but then the compound itself is not aromatic. Let's come to this place. It's the same thing. This is sp3, right? Good. Now, mind you, this one was lost as a proton, H+. The hydrogen was lost as a proton, right? Good. So this is sp3. Now, this is perfect because it has 6 pi electrons. So it is perfect. So the only problem we have here is that it's sp3. That has made it not conjugated. It's not fully conjugated, right? Good. Now, the hydrogen here is lost as a negatively charged ion. Negatively charged ion. And so it means it takes the electrons away. When you take the electrons away and leave the positive charge here, what happens is that the hybridization here changes to sp2. Now, when it changes to sp2, it has unhybridized p orbital to overlap, so it can be conjugated. The electrons here are already 6 pi electrons, right? So it can just be aromatic like that. So it turns aromatic. So that cycloheptatrienal cation cation is aromatic. So let's take note of it. It can be confusing and all, but then let's take note of that. This is very simple. So this is aromatic, this is aromatic. Their compounds are not aromatic, but their ions are aromatic. Very simple, right? It's an anion for the pentane, this cation for the heptane. Very important. Good. And then let's take the form by which hydrogen can leave. It can leave as a proton, can leave as a negatively charged, as electron, negatively charged species. It can leave as a radical. Very simple. Okay. Good. Now we are talking about the heterocycles, right? Good. So pyro is a heterocycle. Realize that the ring has more than just carbon. There's nitrogen in the ring. Pyridine also has more than just carbon. There's a nitrogen in the ring. So that is the heterocycles we are talking about. Now both of them are aromatic. Let's explain the aromatic nature of them. So the carbons here and the nitrogen are sp2. The nature of this hydrogen, which is a question that can come, is this nitrogen is sp2. This nitrogen is sp2. So they are both sp2. sp2, right? Good. Now the lone pair here has been contributed to the system, the ring system, right? So it's not available. So this is a very weak base. Because the lone pairs are not available, it's a very weak base, right? Very, very, very weak base. Not like this one. This one, the lone pairs are available, but this one, the lone pairs have been used to contribute to the aromatic system, right? So a very weak base. And then if it's acting as a base, it will affect the aromaticity. So it doesn't prefer acting as a base because when it's aromatic, it is stable. No compound will want to move to an unstable state. That is the whole idea, right? That's the whole idea. Good. So it has 6 pi electrons. 1, 2, there's 2, 4, 6. 6 pi. 2, 4, 6. So that's it. So it has 6 pi electrons. It's sp2, and then it's conjugated and all the properties is planar, you know. Now this one, the nitrogen is also sp2. The electrons, lone pairs have not been contributed, so they are available to act as base or any other property, right? And then we have 6 pi electrons, so it's also aromatic. So examples of heterocycles which are aromatic, we have pyrrole. It would be very beneficial if you can draw pyrrole, right? Draw pyrrole and then be able to also probably draw pyridine. So that when you are asked to give examples of heterocycles which are aromatic, you can easily give them. Now, they are heterocyclic analogs of naphthalene, right? That is, we have double ring because naphthalene is 2 benzene rings fused together. Now, there are heterocycles which are also 2 rings fused together, right? Fused together, which are also like naphthalene, so might exhibit some properties of aromatic properties. So, example, we have quinoline, isoquinoline, indole, and purine. So we can take note of these examples and then at least one of the structures. Good. Now a question for us to try. We are seeing that cycloocta 1357 tetraene readily reacts with potassium metal to form the stable cycloocta tetraene dianion. Say, so explain why the reaction occurs readily. One of the reactions is occurring to form a more stable product, and we are learning aromatic compound. This is very simple. That is because the product here is aromatic. It's aromatic. Yes, we can show why it's aromatic. This one has 8. It does not obey the Hückel's rule. This is anti-aromatic, actually. But then when we gain 2 other electrons, it becomes 10, right? It becomes 10 pi electrons. And then once it is 10, it's obeying the Hückel's rule, right? It's obeying the Hückel's rule. Once obeying the Hückel's rule, we are thinking of the fact that it is aromatic, right? So it goes so readily because every compound wants to be stable. So it's acting readily because it is getting stability from that reaction. Right? So it's so readily because it forms a compound or a product which is aromatic because it obeys the Hückel's rule. Very simple, right? Now I ask you, what is the shape? The shape is planar. Once aromatic, it is planar, right? Yes. And then why? So why you can explain the fact that they overlap. Each of the atoms, they are sp2 hybridized. They have unhybridized p orbitals which will overlap, right, with each other, the neighboring ones, and form a molecular orbital which is planar in shape, and which will allow subsequent delocalization of electrons. You can just see something around that, and then you'll be fine, right? This is how simple organic chemistry can be. Good. Now, the next chapter is around the reactions of aromatic compounds, which will be captured probably in a different video. If you have any questions, see any member of the academic board to help you. Thank you very much for your audience, and I wish you the best.